Let's look at an example of Green's theorem. Let's let the vector field f be given by y comma x squared, and let R be the region in the first quadrant, which is bounded by the coordinate axes and the parabola y equals 4 minus x squared. In this example, I want us to verify that Green's theorem holds by evaluating both the integral around C of f dotted with ds and the double integral over R of dn dy minus dn dx, and checking to see that we'll get the same numerical answer. So Green's theorem is telling us that these two are going to be the same. I want us to verify that by actually carrying out the integration and seeing we get the same thing. So the integral around, well, first of all, let's look at the region. It's bounded by the coordinate axes, which are y equals 0, x equals 0, and this parabola. Notice that this parabola, y equals 4 minus x squared, is going to cross the x-axis at 2, also at negative 2, but that's not in the first quadrant, and it has a y-intercept of 4. So that over here on the left-hand side, when we carry out this integral, we're going to have to integrate along 3 curves. We'll have to integrate along the x-axis, we'll have to integrate along the parabola, and we have to integrate along the y-axis. So I'm labeling those C1, C2, and C3, and notice that I'm orienting them so that I'm going in a counterclockwise direction. So over here on the left-hand side, I'm going to have to integrate along those 3 curves and add the 3 answers together. Over on the right-hand side, I'm going to be carrying out a single integral over this region R. So I'm going to leave this picture and the definition of the vector field up, and I'm going to erase the statement of the problem. This is going to be kind of a lengthy problem, so I'll split it over 2 videos. In this video, I'll carry out the integral around the boundary, and in the next video, I'll do the integral over the interior. So right now, let's find the integral of f dot over ds around C, which is going to be the integral along C1 plus the integral along C2 plus the integral along C3. So one at a time, we'll parameterize the boundary curve and then substitute in. So let's start off with C1. C1 is a segment along the x-axis, and the x-axis has equation y equals 0. So all along C1, the y-coordinate will equal 0. So when I parameterize, y is 0, and I may as well just let x equal t. To start at the left endpoint and end at the right, I let t start at 0 and end at 2. So t goes from 0 to 2. So my parameterization, sigma 1 of t, is going to be t comma 0 as t goes from 0 to 2. Now remember, little vector ds is given by sigma prime of t dt. Notice that I'm writing this as sigma 1 to correspond with C1. And sigma 1 prime, that's the derivative of this, is 1 comma 0. So the formula for ds is 1 comma 0. I also need to evaluate f on this parameterization. So f is equal to y comma x squared, but y is equal to 0, and x is equal to t. So substituting t for x, when I substitute the parameterization into f, I get 0 comma t squared. So the integral along C1 of f dotted with ds is going to be the integral from 0 to 2 of 0t squared dotted with 1, 0 dt. Well, look at that. 0t squared dotted with 1, 0 is 0 plus 0. And the integral of 0 is equal to 0. So let me make a note here that the integral along C1 is 0. Now we need to do this again for curve C2 and for curve C3. We might expect that C2 is going to be the most complicated since the other two are straight line segments. Now C2 is a piece of y equals 4 minus x squared. Since this is graphed over the x-axis, one parameterization would be to set x equal to t and y equal to 4 minus t squared. So I'm setting x equal to t and substituting that in here to get that y equals 4 minus t squared. So my parameterization sigma 2 of t is t comma 4 minus t squared. Now I want to start at this right endpoint, which is when t, or x, is equal to 2. So notice that when t is 2, I'm at 2 comma 0. So that's my starting point for t. And I want to end at the point 0, 4. So that will correspond to setting t equal to 0. When I set t equal to 0, I get 0 comma 4. So in order to move from right to left along this curve, my bounds will be from 2 to 0. Now once again, we'll calculate ds, which is sigma prime of t dt, sigma 2 prime in this problem. Differentiating this, that's 1 comma negative 2t dt. And let's also see what happens when I substitute the parameterization into f. The formula for f is y comma x squared. And be careful here. Always make sure that you're substituting the parameterization into f rather than the derivative. Sometimes folks will pull the x and y from here, but you really need to pull the x and y from the original parameterization. So in the original parameterization, y is 4 minus t squared, and x is equal to t. So the integral along C2 of f dotted with ds is going to be the integral from 2 to 0 of 4 minus t squared comma t dotted with 1 comma negative 2t dt. Now if we like, we can swap these so that the 2 is on the top and the 0 is on the bottom. We just have to put a minus sign in front. So it'll be this will be negative the integral from 0 to 2 of, and now let's carry out the dot product. I have 4 minus t squared times 1, which is 4 minus t squared, plus t times negative 2t, which is minus 2t squared. So simplifying a bit, this is negative the integral from 0 to 2 of 4 minus 3t squared dt. Let me pause for just a second. I have the feeling that I've made a mistake. I just want to make, oh, I sure have. You guys have probably been looking at this for a while. I need to come back and fix it. Notice that I had an x squared here, which would have meant that this is equal to t squared at this point. And then t squared times negative 2t is negative 2t cubed. Good for you if you noticed that mistake before I did. So let's go ahead and carry out that integral then. There are no like terms to combine. I will have negative 4t minus a third t cubed minus 2/4, which is minus a half t to the 4th, taken from 0 to 2. So when I plug in the 2, that gives me 8 minus 8/3 minus 16 over 2 is 8. And when I plug the 0 in, I get all zeros. The 8's cancel, and the opposite of negative 8/3 is positive 8/3. So the integral along C2 is 8/3. And now we just need to do the integral along C3. C3 is a piece of the y-axis, which has equation x equals 0. So when we parameterize it, the x-coordinate is going to be 0. And we can set y equal to t. So sigma 3 of t is 0 comma t. But I want to integrate from top to bottom. So I want to start off when t is equal to 4 and stop when t is equal to 0. So that'll start at the point 0, 4 and end at the point 0, 0. ds is sigma 3 prime of t dt. Differentiating sigma 3, I get 0, 1 times dt. I need to substitute the parameterization into f. F is y comma x squared. Substituting in y equals t and x equals 0, I have t0. Oh, and we can see that that dot product is going to equal 0 again. Integral along C3 of f dot of the ds will be the integral from 4 to 0 of t0 dotted with 0, 1 dt, which is the integral from 4 to 0 of 0 dt, which is 0. So the integral along C3 is 0. So just putting it together, for the left-hand side, the integral around C of f dot of ds is equal to 0 plus 8/3 plus 0, which is 8/3. Now in the second part of the video, we'll look at the right-hand side, which is the double integral over r of dm dx minus dm dy dA, and verify that we get this exact same answer.